All right, so if we've got our reaction, we looked at this yesterday, we've got hydrogen plus iodine, and initially all we have is just pure reactants, hydrogen and iodine. So we are starting with those concentrations up top, right, with a lot of those. The hydrogen iodide, the products, we don't have any to begin with, okay? So that concentration is starting down here. Now, as we start the reaction and these bonds break, all right, those particles, all right, might end up finding each other. And so as the reaction proceeds and we get more product formed, we start to see the product concentration increasing. What's happening to the concentration of the hydrogen and the iodine as the reaction goes forward? Does it go up? Does it go down? Does it stay the same? Goes down, right, okay, because we're using it up. So that concentration is going to be diminishing. And like we saw with the demo yesterday with the green water going back and forth, eventually we reached a point where we still had a transfer of the liquid, the green water, from one to another, from one beaker to another, but the net amount that was present, right, was the same. It wasn't that they were the same volumes, all right, but it was the rate at which we had 50 milliliters going in each direction both times, okay? So that's the equilibrium. So when we talk about it at equilibrium, it's not the amounts that are the same, it's the rates. The rates of the forward, so that's the kind of reaction that we're used to, the forward reaction, okay? Initially, that's all that's happening. But as that product starts to form, okay, it's almost as if, all right, the reverse reaction starts to speed up. And the longer it goes, as they approach equilibrium, essentially, those arrows become equal, right, representing the equal rates. So whenever you see that double arrow, the double arrow means that we have what's called a reversible reaction. It just means it can go forward and it can go backward. And reversible reactions, left undisturbed, will eventually come to a state of equilibrium. And equilibrium is where the forward rate and the reverse reaction rate, all right, will be equal. All right. So questions on that, on what equilibrium is? Okay. Now, when we're at that balance, if we mess with that balance, say I added more water to this beaker. If I added more water and I'm still going back and forth with the same beakers, now I'm going to be able to fill this one up more. So as I'm transferring it, this level is going to start to rise. All right, so I'm upsetting that balance. I'm stressing the equilibrium. And that's where LeChatelier's principle comes in. Okay? LeChatelier's principle says essentially that if you have a state, a system that's in equilibrium, and you do something to mess it up, to stress it, the system is going to try and autocorrect itself. It's going to shift however it needs to alleviate that stress and relieve it and establish a new equilibrium. Now, it's going to be at an equilibrium. It's not going to be the same exact one. So in the case of adding more water to the right-hand beaker here, the left, your left, the new equilibrium that's going to be established is a lower amount of my reactant, but a higher amount of my product. So that volume would have come up. Okay? Now, how exactly can we stress the system? Right? Multiple ways. If we change the concentration. Okay, so this is new information now on the slides that you have. Okay? Change the concentration by either adding or subtracting reactants or products. Okay. We can stress the equilibrium by changing the temperature. Now we know that all reactions are either endothermic or exothermic. So one of the reactions, forward or reverse, is going to be benefited by having heat added to it. All right? If it's an endothermic reaction, that would benefit from having heat added to it. If it's an exothermic reaction, it's going to want to go away from that additional heat and use that up. All right? So we'll look at some examples here on your worksheet that will talk about what to do as these concentrations increase or decrease, and what about heating or cooling a solution or a reaction. The last one is pressure. And with pressure, just as we dealt with pressure before, pressure only isn't, has any impact when we're talking about gases, right? Because gases are the only compressible state that we have. So when we talk about that equilibrium being upset, we say that the reaction is going to shift in response to that. And it's going to shift based on what it needs to do to relieve the stress. Okay? So if you add something, whether it's adding a reactant, adding a product, adding heat, the reaction is going to shift away from that addition. Now that it could be to the left or the right, it just depends on where the addition is being made. But when you add something, the reaction will shift away. Add away, AA. That's how you can remember that. And the reason it shifts away is because it wants to use up that excess. If you take something away, if you remove it, all right, it's like digging a hole. You dig a hole in the ground, you dig it deep enough, eventually the dirt's going to start to fall in and fill that hole in. Okay, the reaction will shift, excuse me, towards that removal in order to replenish the supply. Okay, so always think of it in these relative terms. Add something, move away from it. Take something away, move towards it, fill it in. Temperature is the same way. All right, excuse me. As far as gases go, okay, good old Avogadro gave us 6.02 times 10 to the 23rd power. One of the other things that he defined for us is that at the same pressure and temperature, any gas, 1 mole of it, Avogadro's number worth of it, is going to occupy a volume of 22.4 liters under standard conditions. So about 11 Pepsi bottles full. Okay? That being said, there's a relationship between moles and volume. And so therefore, if we put a gaseous reaction system under pressure, we squeeze it. When you squeeze something, you force it into a smaller volume. So when you increase the pressure, the reaction, the equilibrium, is going to favor the side that's going to take up the least amount of space. In other words, has the fewest moles of gas. So you look at the coefficients and you add up how many moles of gas you have on each side. If it's increasing pressure, you push to the side that's got the fewer number of moles. Decrease the pressure, go to the side with the greater number of moles. All right? So let's take a look. Curtis, would you pass these out, please? Thank you. There we go. So we're going to take a look at some examples here. Now, this is an abbreviation of what you have on your worksheet there. And we're really just going to focus on what is happening with the 3 species that are involved, the nitrogen, the hydrogen, and the ammonia, in terms of when the system is stressed, how is it going to respond to that? Thank you. All right, so first off, just looking at the equation itself, do we have an endothermic or an exothermic reaction? Exothermic. How do we know, Bryce? Okay, the energy term is on the product side. We know that on the product side it's being produced, and that's what we have with an exothermic reaction. All right, so in the first one, okay, you have the example at the top of the paper there, so this should be the second one down, I believe, right? If we add hydrogen, okay, so if our stress is we're going to increase the amount of hydrogen, we're going to pump more hydrogen into this system. When we add something, the reaction is going to shift away from that addition in order to use up that extra that we have. So in this case, the equilibrium is going to shift to the right. Right? So in that first column where it says equilibrium shift, you're going to write right. Okay, and the hydrogen is what we are stressing, so we're not going to put anything in that block. But if we're moving to the right, that means the forward reaction is the one being favored. So what's going to happen to the amount of nitrogen? Is it going to go up? Is it going to go down? Is it going to stay the same? Bryce? It's going to go down. Because if the reaction is moving forward, that means we're making ammonia. Well, to make ammonia, you have to use up hydrogen, but you also have to use up nitrogen.
All right, so this is just the way the whole day has gone for me. But technology-wise, things have just been going. So anyway, obviously the original video that went along with the board work cut out, so you're going to benefit from this because I can go through and edit out some of the low spots, the delays, and shorten things up for the rest of this, make the clip speed go a little bit faster, and I'm just going to provide narration as we go. So buckle up, we're going to finish out the equilibrium LeChatelier's principle and then talk about catalysts, and we'll have you out of here in just a few more minutes. All right, here we go. So as the hydrogen is increased, right, the nitrogen, because the reaction is shifting away from the added hydrogen, that means that nitrogen concentration is going to decrease, and those brackets just refer to as shorthand for concentration. And so because we're using up the excess hydrogen, the nitrogen is going to decrease. Because it's shifting to the right, the ammonia concentration will be increasing because it is being produced. All right, in the next step, if we talk about stressing the system by increasing the amount of ammonia, that means that we are going to shift away from the addition, which means the equilibrium, the reaction will shift to the left. And if it's shifting to the left, that means that the amount of nitrogen that is being produced is going to increase, and the amount of hydrogen that is being produced is also going to increase. And we don't put anything for ammonia because that's the stressor. If we now think about removing something, stressing the equilibrium by removing it, then what that means is we're creating a deficiency, we're creating a gap. So equilibrium is going to shift to try and reestablish that amount or replenish that missing amount. So removing nitrogen is going to have us actually shifting the equilibrium, the reaction to the left to reestablish equilibrium, which means that hydrogen is going to increase and the ammonia will decrease because it's being used up. We can also look at the impact of heating or cooling a reaction and affecting the temperature, and we treat temperature as if it were any other substance. Okay, so if we talk about heating a reaction up and increasing the temperature, it means we're going to increase the energy component. Now this is an exothermic reaction because energy is on the product side. And so if we increase the temperature, when we add something, we shift away. So we're going to shift to the left in this case. And shifting to the left means that both the nitrogen and hydrogen concentrations will increase. The ammonia is going to be used up and it's going to decrease. Besides affecting concentration and temperature, if we are dealing with a reaction that's happening in the gas phase, pressure is also an influence. So when we talk about pressure impacts an equilibrium or stresses an equilibrium in that the reaction will be favored. If you're increasing the pressure, it's going to be squeezed into the gas, it's going to be squeezed into a smaller volume. And so when it comes to gases, 1 mole of any gas has a volume of 22.4 liters. So the fewer moles you've got, the less volume it takes up. So in this case, we've got 4 moles of gas total on the reactant side, 2 moles on the product side. And so if we increase the pressure, it's going to favor to the right side because that's where you have fewer number of moles of gas. And then the ammonia is going to increase because of that shift to the right. Whew. Take a breath. All right, next up, catalysts. All right, so a catalyst. A catalyst is another chemical compound. It's a substance that you add to a reaction that's going to help out that reaction. It's going to help the reaction to proceed, usually by speeding it up. All right. Now, when we talk about its effect on reaction rate, it's going to increase. Now, if we think about a reaction profile, we know it's got the characteristic shape where you've got your reactants to start, and then you have that energy hill that has to be climbed, and then your products. And this one you should identify as an endothermic reaction because products are higher than reactants. The difference between the reactant energy level and the height of that hill is the original activation energy. Okay? What a catalyst does is it actually helps the reaction go faster because it cuts that hill down. It decreases the required activation energy necessary for the reactants to break their bonds and then rearrange and form new bonds and make the product. And so catalysts are great for helping reactions go faster, but in terms of equilibrium, it does nothing for equilibrium. It doesn't make any change at all, because not only is it helping the forward reaction go faster by lowering the activation energy, it's also lowering the activation energy for the reverse reaction. And so they both benefit from the use of the catalyst. So in terms of equilibrium, yeah, you get there faster, but there's no overall change.